Bismillahirrahmanirrahim. Okay, we are here today for the Lab 3 session, Microstructure Examination. If you remember from the last week, we prepared the specimen or the sample for microstructure examination. In the last week, we did the sample preparation by 5 steps. What were the steps? Those were number 1, cutting, number 2, mounting, number 3, grinding, 4, polishing, 5, etching. So after etching, in the lab experiment video, we had the number 6 step, which is examination in the microscope. So that is what is today's lab, microstructure examination. Okay, let's go ahead in this. So in the microstructure examination, we have when you put the sample after etching in the microscope, you will see a structure like this, or there can be many variations for this. Okay, but generally the structure will look something like this. Okay, it is. So what is a microstructure? Microstructure is made up of multiple grains. So it's like a grains, spots, or بالعربي hub. Okay, it has small pieces separated by what? It is separated by grain boundaries. Okay, grain boundaries. The lines you see here, which are separating white and black spots, these lines are called grain boundaries. Very important. Okay, and the microstructure can be seen through microscopy. So you use a microscope to see the microstructure by using magnifying lens. Okay, what does the magnifying means? Magnifying means zooming in. Okay, you can zoom in into the microstructure up to 100 times, 300 times, 500 times, or as much as you want. If you go for electron microscope, you even go further inside the microstructure. But for now, using a normal magnifying microscope, you can use to see the microstructure. Okay, in this lab, what will happen is I will give you a microstructure, and all you have to do is to find out these 4 pieces of information from this microscope or from this microstructure. So a picture will be given to you similar to this one on the right side, and I will ask you to give me 4 pieces of information. Number 1 is phases present. So what are the phases present in the microstructure? Number 2, what is the percentage of each phase present in the microstructure? Number 3, what is the grain size? The grain size is just like a diameter or a size which you will measure by a method. And number 4, the phase distribution. Phase distribution is the how different phases are distributed. So these are the 4 information I want you to study for the given microstructure to you. How you will study this? This is the lab about, and I am going to teach you and go through each of them one by one. Okay. So what is phases? Let's go for that. Okay. So steel, the material steel has, if you look into the steel microstructure, it has many phases. The names of those phases are very new to you, and what are they? They can be ferrite, number 1. It can be cementite, number 2, or it can be, there's a third one also called pearlite. Okay, so the 3 phase names are ferrite, cementite, and pearlite. Okay guys, the first steel phase I have is called ferrite. Ferrite is usually, it's looking like a white grain area. So the white region here on this microstructure you see is ferrite. What is the properties, or what is the information we can get from ferrite? Ferrite has a low carbon content inside it. So and it is very soft. It has soft mechanical properties. How you can know? The composition of ferrite has less than 0.021% of carbon inside ferrite. Okay, less than 0.021% of carbon inside ferrite. That's why it is soft mechanical properties. What do you mean by mechanical properties? It means if you try to bend it, it will bend because it's soft. If you try to break it, it will break because it's soft. So anything you want to do physically with ferrite, it will be soft in nature. And remember, ferrite is white grains in the microstructure. Now let me come to cementite. So these are the two extremes. Cementite has high carbon content and it has the percentage of carbon as 6.67%. Okay, so this, because it has more percentage of carbon, it has hard mechanical properties. So it is very hard for working and bending and breaking. Okay, how does the cementite look like? The cementite looks like white lines. So actually cementite is lying in the boundary area, but remember, it will have white color, and it's also a little bit thicker than the normal grain boundary here. So cementite looks like this. And the third one, which is perlite, it's black color. Actually in this picture, this microscope, the black area is perlite. Let me come to the perlite in the next slide. And one thing before going to next slide showing you perlite is that cementite is only the lines area, okay, not the black area. What is black area? Let me show you that. So black area is called perlite. Perlite phase is what? Perlite is a mixture of ferrite and cementite. Okay, so you know ferrite is soft and cementite is hard. So what will happen if you mix something hard and soft? It will become medium mechanical properties. So it is acting in the middle. If you come closer to the black area and go even more deeper, so this is by even deeper microscope, you will see the white and black lines. So this is actually cementite and ferrite repeating them. And when you look from normal magnification, it will look like this black region. Actually, this microstructure, the first one given here on the top, has ferrite here, which is white, and some perlite. These black areas are perlite. So some perlite are here and some ferrite is here. This second microstructure is has perlite in this center and cementite around it. Okay, remember. But in order to generally remember these three names, you need to remember it like this. Ferrite is white color grains, perlite is black colored grains, and cementite are white lines around the grains. Okay, just remember it like this. And this will keep also one more thing is ferrite is soft, cementite is hard, and perlite is medium. Okay, remember these things and inshallah you will be good. So Dr. perlite, in the picture shown here, it's a microstructure. I have around 75% ferrite in this picture and 25% perlite in this picture. There is no cementite here. Okay, this percentage are only from our observation from a normal eyes, and it can be 60% and 40%, it can be 70-30, it can be 50-50, but this is just a general observation. What I want you to observe is to first find out what are the phases present from the perlite, cementite and ferrite, which one is here and which one is not. So clearly we can see we have ferrite and perlite and cementite is not here. Let me show you again the example of cementite so you remember. If you can see, cementite is here. I will bring it on this slide so we can compare. This one now on my left side, on my right side is the cementite and perlite. Okay, this one black area is the black area is perlite and the white lines are cementite. When you have cementite, it will always or sometimes always coming with perlite. Okay, remember. And also cementite is a little bit thicker line as compared to grain boundaries. If you can see here, the black grain boundaries here are very thin and it's almost like a line. But cementite is like a broken thick passage here, if you can see this. So this is how you recognize there is cementite inside or not. Okay, So cementite is looking like this, while this one. So now if I tell me the percentage of cementite and pearlite in the picture on the right, let's hear some of the observations from you. So in this example, from our, again, human judgment and from our observation, maybe we can say we have 20% cementite in this example and 80% pearlite, because it's mainly pearlite here. Okay, now you know about how to get the percentage by general observation and how to find which phase is present. Let me take you to the step number 2, which is called percentage of each phase. What is that? So the percentage of each phase, let me explain it to you and then I'll come to your questions. You find the percentage of each phase because you want to find out that which region is your microstructure falling in. Okay, if the region, there is, from the selection of 3 regions, we have 3 options. Option number 1 is hypoeutectoid. This is one option. The middle option is eutectoid, and the extreme option is hypereutectoid. Okay, so it's like 1, 2 and 3. So what is hypoeutectoid? This is the new names. I know it's difficult to understand these new names in the beginning, but inshallah with practice and with writing more, you will remember these words more. But I want you to know what will happen if a microstructure is hypoeutectoid and how it will behave mechanically. So let me go into detail. Hypoeutectoid is the beginning phase where the steel has carbon less than 0.8%. Okay, it's very important to remember, anything less than 0.8% carbon inside the steel is called hypoeutectoid. So it is mainly ferrite, because if you remember, ferrite phase, if you have more ferrite phase, it means that's it's all less than. So how much was the percentage in ferrite? Ferrite has less than 0.021%. So even if you have some ferrite mixed with pearlite, it will still have, if the carbon percentage will be less than 0.8, this is called hypoeutectoid steel. Okay, remember. So it is mainly, so what you will find in the microstructure of hypoeutectoid steel, you will find ferrite and pearlite phases mainly. These two will be there, and then this you can say it's hypoeutectoid. If more ferrite percentage means softer steel. So mainly hypoeutectoid steels are soft in nature. This is just like a reinforcement of the same information you get in the previous slides, where when I said ferrite is this much and it's softer, but it's a different name, okay, or a different category of steel they divide in. If you can check this picture, this is the first picture on the left here. This is hypoeutectoid steel. Why? Because it is all ferrite. There is no pearlite inside, and it means carbon is less than 0.8%. If there is ferrite and some pearlite inside, also ferrite. So this is also inside the hypoeutectoid region. Okay, remember this too for hypoeutectoid. Ferrite, all ferrite is also hypoeutectoid, and ferrite plus pearlite is also hypoeutectoid region, which means it's soft steel. Coming over to the number 2, which is eutectoid steel. Eutectoid steel. In the eutectoid steel, which is the second category, the carbon content is at the border of 0.8%. Okay, it is equal or almost equal to 0.8%, which means what? It is only pearlite phase mainly. So if in the microstructure you only see pearlite is black color, you will find it is called eutectoid steel, which means it has medium properties. Okay, simple. If it is full pearlite, it is eutectoid steel. It is very difficult to find, by the way, eutectoid steel. And the last category, which is hypereutectoid. Hyper means increased inside. So it has carbon content more than 8% and up to 2%. How it will happen? It will be a combination of pearlite and cementite phases. Okay, and you can see example of that here on our right side. It is very hard in nature because the carbon percentage is now more. So it has pearlite and cementite, you can see in the middle. So if you have pearlite and cementite combined, it will have carbon percentage of 0.8 to 2%, which will give you a harder steel. Okay, let me try to give you an actual microstructure to give you examples of these, and let me paste them on this slide. Okay guys, here I have on my left side one microstructure and on my right side another microstructure. Here the percentage of each phase in this one on the left side, this microstructure. How to answer this question? You can answer this by saying, in this microstructure I have 80% ferrite phase, which is white color, and I have around 20% pearlite phase, which is black color. So because of that, ferrite and pearlite, it is hypoeutectoid steel. And in the hypoeutectoid steel, my carbon percentage is less than 0.8%. That's how you answer this question. For the one microstructure on the right side, how do you answer this question? What are the percentage of each phase in the microstructure on the right side? So in this microstructure on the right side, I have two phases which are black one pearlite and the white lines which are cementite. So, but looking from my normal eyes, I can see, or my judgment, I have 80% pearlite and maybe 20% cementite, and this will be falling in a region of hypereutectoid, which is this one. And in the hypereutectoid, you have the carbon percent ranging from 0.8 to 2%. That's how you answer this question of find out the percentage of phases present in a microstructure. Okay, after this, the third piece of information I want you to find from the microstructure is the grain size. The grain size is simply the size of the grain, and there is two methods to find it. So let me show you what is grain size. Okay, the grain size, why we need to know the grain size? Because the grain size will also give you good information about how the material will behave. Okay, the grain size also changes the mechanic or affects the mechanical properties of the material. Okay, fine grain size has stronger, or you can say stiffer, stronger properties compared to coarse grain size. Coarse means big size, so, and fine means small. Okay, if the grain size is like this, you can see on the chart on my right, number 1, 2 and 3, you can see the size of grain is really big. If the grain size is big, it will have weaker properties because these grains can slip on top of each other. But if the grain size is very small, like this one, 6, 7 and 8, it's very small and they are really packed inside each other, it will have a stronger properties mechanically. Okay, very easy to remember. Why? There is methods where you can make the grain size from big size to smaller size. How you can do it? There's many techniques. It's called severe plastic deformation, alloying, mixing some other metals, and also thermal techniques or heat treatments. And using these treatments, you can bring the size to be smaller. Why you want the grain size to be smaller? Because it will have stronger properties. The grain size can be found by two methods according to American Standards for Testing Materials, ASTM. There's two methods to find grain size. The method number 1 is direct comparison. Method number 2 is intercept method. Okay, let me show let me show you both of them one by one. Okay, here is something important information before going into the calculation of grain size. It is something which confuses students a lot. The grain size does not mean this is the diameter of your grain. Okay, because if you can see this table, this is we use this table to find out the grain according to the grain size number. Okay, you can see the grain size number 1 is bigger grains. The grain size number 2 becomes smaller as you go increase it. The grain size, if the grain size number is 8, it means the grain size is really small. Okay, how you can find it out? You can see it here. If I see the grain size for grain size number 1, it means my diameter of the grain, average diameter, is 0.25 millimeter. But if my grain number is 6, the average diameter is 0.045 millimeter. So as the grain number goes higher, the grain size in millimeter becomes smaller. Okay, this is a confusion which students have, so please clear it before moving on to actually calculate the grain size. Okay, here I have an example of the grain size measurement chart along with its microstructure given on the right side. Okay, sometimes the microstructure which you will take or get from the microscope is not clear enough to do the comparison. So the first method we have, it's called direct comparison method. In the direct comparison method, we just compare the microstructure with the comparison chart. Here in this picture, I have both of the microstructure on the right side and the chart on the left side. Okay, so the direct comparison method will do what? From your human judgment, from your normal understanding, what do you think can be the grain size number when you compare it with this chart? And that's the direct comparison method. You can see here in the microstructure that the gray area is actually perlite. It's not very clear coming. Maybe the brightness or the contrast has got bad here, but certainly I have more perlite here, and these black area here are actually perlite and white area is ferrite. So from your understanding, check an average. So take some grain sizes and tell me averagely what can be the grain size according to direct comparison method. From your response, I think you are saying that the grain size is close to 3. Okay, now what we will do, from your judgment, when you said okay, my grain size is 3, you need to go back to the table and see what is the 3 showing in diameters. Okay, what is the grain diameter in millimeters? In this case, it is coming 125 over 0.125 millimeter. So from grain size table, I have 0.125 millimeter. Is this method of direct comparison very accurate? You guys decide after checking the second method, which is the intercept method. Okay, let's find it out. The second method for finding the grain size is the intercept method. Okay, intercept method, it's called intercept method. How do we do it? It's a 4-step method and you use a formula and some graphing technique to find it out. Let me go through this. You have to do this picture is showing in as an example, but the next picture will show from a real microstructure also. So let's go through this example in the beginning now. So the first step you do in this method for finding the grain size, what you do is you draw 3 circles. I have one circle, it's the smaller one, then I have the second one here, and then the third one here. What is the difference between them? They have the same center point, but the diameter is increasing from 2 centimeter to 4 centimeter to 6 centimeter. Okay, you just draw at any location in your microstructure, just draw 3 circles. Okay, second, you have to take the sum of their circumference. So sum of their circumference is the second thing which you have to take. What is the sum of circumference? So the circumference formula is pi multiplied by its diameter, or the other way is, if you remember, 2 pi r. So what you do is you take the sum of 2 centimeter circle circumference, 4 centimeter circle circumference, and 6 centimeter circumference. You just add them together and you get a number called LT. Okay, remember. And then the third step you have to do is you have to count how many intersection, which is given by NT, between the drawn circles and the grain boundaries. So here you need to count how many grain boundaries are intersecting these circles. So let me give you an example. This is called NT. Let me give you an example by showing you how to count. In this case, if you can see, my circle is intersecting grain boundary here. So point number 1, 2, 3, 4, 5. So first circle is intersecting at 5 points. Let's check the other one. 6, 7, 8, 9, 10, 11, 12, 13. So 13 in total now, and let's count the last circle. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 here and 25 here, 26, 27, 28. Excellent. So my NT value is 28. Remember, yes, I agree that counting the points is also human judgment, and this can have an error here. So, but there is a trade-off in both methods. So the points which is intersecting the grain boundaries is the number you have to find. Once you have this number, you can simply use in the step number 4 this formula, which is the grain number. So G value is the grain size number. Remember, it's not the diameter, it's the grain number. You have to write minus 10 plus 6.64 and then the logarithm of this number, which is NT. NT is the number of points intersecting, multiplied by M. What is M? I will tell you. And divided by LT. LT is the sum of all the circumference which you find here in the step number 2. So M is the magnification of the microscope. This M will be given to you. It's constant. In our cases, we use as 100 times bigger. So the LT unit must be in centimeter. This is very important, guys. This LT with the circles you will draw, the unit should be in centimeters. So generally, what is intercept method? You will draw 3 circles of any size. I used to draw 1 centimeter, 2 and 4. You can also draw 2, 4 and 6, up to you. Then you take sum of circumference of the circles. Third, you count how many points it is intersecting the 3 circles in the grain boundary. And fourth, you just plug the values in formula using the M value, which is the magnification value. I hope it's clear. Let's look at a real life example and see and study it more. Okay, let's come to see this microstructure given on the right side. I have drawn already 3 circles of 2 centimeter, which is this one, and then 4 centimeter and 6 centimeters on my micrograph or microstructure picture. So the first thing I will do is calculation of circumference length. I have pi multiplied by 2, by 4, by 6, and it gives me 37.7 centimeters for the circumference of these circles. Remember, the center point of all the 3 circles is the same, which is here. Okay. The magnification, the M value I am using in this microstructure is 100 because it is the 100 times zoom in. So my M value is 100. So what's the last thing remaining in the formula? It is the NT value, the number of times it's intersecting the grain boundaries. So we will count the location where the grain boundary is intercepting these 3 circles. So NT value is done in 3 steps. So this guy is saying I have 6 points intersection in one circle, 19 in the second, and 23 in the third one, which will total out to be 48. Let's try to count maybe circle number 1. And this is how also you will show me in your lab report by mentioning where are your points. Okay, so let's count it here. Let me start from bottom. I have maybe one green boundary here, 1, and another one here. You can see white and black. Usually the grain boundary is between white and black, so it's easier to find. This will continue in white until it reach here. This is another grain boundary, white. And then I have another grain boundary here. I have one grain boundary here also. So let me put it here, grain boundary. And then another grain boundary here. I have another grain boundary here. I have one more intersection here and another intersection here. So, and this one is all in white. Maybe here there is another one. So this is your judgment. As the microstructure is clear for you, you can try your best to catch the grain boundaries visible to you. Okay, and then show me how many points in circle 1, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I managed to find 9, while in our example it is 6. So clearly there is some error which we can have when we are counting the points. Okay, once you have these numbers, what you have to do is put them in the formula: minus 10, 6.64 log nt multiplied by m divided by lt. So our nt value, the number of intersecting points, is 48, magnification is 100, and the circumference total is 37, which gives me the grain size of 3.98, which is approximately 4. So from the table we can say that the grain size is 0.09 millimeter. So this is actually your grain size in millimeters, average diameter of the grain size, because my grain number is 4. And is this method more accurate than direct comparison? It is up to you how you justify it. Okay, the last piece of information I want you to find in your microstructure is the phase distribution. Yes, the last piece of information you need is phase distribution. This is simple step. You just need to find out that is your phase distributed uniformly or is it non-uniform. There can be only two options for that. The phase distribution can be uniform or non-uniform depending on the type of microstructure you have. So all the examples which I have shown you in the previous slides is the example of uniform distribution. Okay, and everywhere the microstructure is looking the same. The grain size distribution and the phase distribution is the same. It's homogeneous. If you change from one place to another place on the microstructure in the microscope, it will have the same distribution. This is the uniform distribution. But there are cases when you have non-uniform distribution in the microstructure. For example, you see here on the right side, on one side I have all here perlite, but as I move towards right, there is cementite coming in the microstructure. Can you see that? Here on the left side I have all perlite, but on my right side here there is some cementite or white, maybe it's ferrite, is coming in the microstructure. So you can see clearly there is this difference between the two. Also in this example at the bottom, you can see here everything is white on the right side, while on the left side there is some black perlite coming in. Why? If you see this example, also you can see this is totally white, then you have some percentage of perlite inside, then you have more perlite, then more perlite, and then this is totally perlite or totally another material. So why there is a gradual or there is uneven or non-uniform distribution? We have these, or they are also called functionally graded sometimes, like this one. They are here because sometimes in an application where you're using the steel, you need something very hard from the surface and soft from inside. For example, the gears or the cutting knife, you need the tip to be very hard and inside you need to be very soft. So it depends on the application. Sometimes non-uniform microstructure distribution is what you need. But the thing which you need to remember is that uniform distribution will have distribution everywhere the same, while the non-uniform microstructure distribution will have changing or there is something irregular in that. Okay, that's all you need to find out from the given phases to you. Most of the phases we give you is usually uniform. That's what you need to find out. If you need to know anything more in this regarding microstructures, you can always refer to these resources which will give you more information on this lab. And that's all I have to tell you in the microstructure examination lab here.